If you tie inflated balloons together at the knot, they automatically push away from each other to grab as much 3D space as possible. Molecules do the exact same thing. Electron groups naturally repel each other, pushing apart until they hit a stable geometric shape. We map this physical spacing using the AXE formula. A represents the central atom, X stands for the outer bonded atoms, and E accounts for empty space, specifically the invisible lone pairs of electrons that aren't bonded to another atom. Look at this chart, which catalogs these molecular geometries. The top row shows the simplest scenario, AX2E0, one central atom, two bonded atoms, and 0 lone pairs. To maximize distance, the two atoms split the space evenly, forming a linear molecule with a 180-degree bond angle. Add a third bonded atom, moving down to AX3E0, and the space divides into thirds. The atoms form a flat triangle, a trigonal planar shape with 120-degree angles between them. When every electron group around the center is a physical bonded atom, determining the molecule's shape is just basic division of a 360-degree sphere. But the geometry changes completely when an electron group isn't tethered to an atom. What happens to the shape when you introduce a lone pair of electrons? Lone pairs don't have a second atomic nucleus to stretch them out. They act like a fat cloud of negative charge, clustered close to the central atom. This wide cloud takes up more physical space, actively pushing the remaining bonded atoms away from it and squeezing them closer together. We can see this squeezing effect clearly on the chart. Here is the baseline for 4 bonded atoms, AX4E0. They arrange themselves into a 3D tetrahedron, spacing out at exactly 109.5 degrees. Swap one of those solid atoms for a lone pair. The fat electron cloud presses down from the top. The tetrahedron warps into a trigonal pyramid, and those ideal 109.5-degree angles are crushed down to 107.3 degrees. Drop another solid atom and add a second lone pair, and the squeeze compounds. The two fat clouds force the last two bonds into a tight bent shape, with the angle shrinking even further to 104.5 degrees. The atoms you can actually see are only half the structure. The invisible lone pairs are dictating the final shape by crushing the ideal geometric angles. With 5 bonded atoms, the geometry gets crowded. The trigonal bipyramidal base has 2 distinct positions, 2 axial atoms sitting at the poles at 90 degrees, and 3 equatorial atoms forming a ring around the center at 120 degrees. If we remove one atom to make room for a fat lone pair, we have a dilemma. Does it take the 90-degree axial slot or the 120-degree equatorial slot? It needs physical room. It claims the 120-degree equatorial slot, where it has the most space to expand. This knocks the molecule off balance into a seesaw shape, severely compressing the remaining angles. As we continue to swap atoms for lone pairs, they keep filling that equatorial ring. 2 lone pairs create a T-shape. 3 lone pairs fill the equator entirely, forcing the remaining 2 atoms back into a straight line. Returning to our chart, we see the final major baseline shape, 6 bonded atoms. This forms an octahedral geometry, characterized by perfect 90-degree symmetry across the board. But just one lone pair destroys that perfect symmetry. The cloud forces the remaining 5 atoms slightly upward into a square pyramid, squeezing those 90-degree angles down to 84.8. Geometric stability in complex molecules is a game of survival. Lone pairs will reliably force their way into the positions that offer the widest possible angles. Let's apply these rules to map out a real molecule, sulfur tetrafluoride, or SF4. We start with sulfur in the center, assigning it A. It is bonded to 4 fluorine atoms, giving us X4. That leaves one unbonded pair of electrons on the sulfur, our single lone pair, E1. We translate AX4E1 by combining the components. 5 total electron groups means a trigonal bipyramidal base. The single lone pair grabs an equatorial spot for maximum space, leaving us with a final 3D seesaw shape. Looking at this entire chart, we can group these shapes by their steric number, the total sum of your X bonds and E lone pairs. That total number determines the base geometry, whether it's linear, trigonal planar, tetrahedral, or beyond. The total count of electron groups provides the initial 3D scaffolding. But to determine the actual shape of the molecule, You have to track the lone pairs. They are the invisible sculptors that squeeze, push, and dictate the physical reality we measure.